Alright, 3, 2, 1. Alright, let's go. So, last time we looked a little bit more at determinants and we established the classic recursive formula, but let's recap everything. So, we have now officially established the existence and uniqueness of a function on the n by n matrices that has the following three key properties. It's identity preserving, meaning that the determinant of the identity matrix is equal to 1. Alternating, meaning that the determinant is 0 when my matrix has two identical rows. And it is row linear, meaning, what is that word? Get out of here. Well, I just noticed that. Also, I don't think corresponding is spelled right, but whatever. Corresponding. What the fuck? Yeah. Great. Anyway, and it's row linear, meaning that it acts linearly with respect to the rows. Again, there's a bunch of different names for this out in the literature, multilinear form, or an n-linear mapping. I've always liked calling it row linear, because it's linear with respect to the rows. Hence the name. Alright. Okay, so we've already established now that there's a unique function with these three properties, and it has a bunch of other neat properties. If you scale a matrix, the determinant gets scaled accordingly with an extra factor of n. This, again, is because scaling a row will scale the determinant, so if I scale every row, I'll pick up n copies of my scalar. The determinant is non-zero precisely for invertible, and this will be the star of the show today, because we're going to get a formula for the inverse. Ooh. The most important fact in all of mathematics, not really, but a very powerful result is that the determinant of a product is the product of the determinants, which actually gives us a neat little formula for the determinant of the inverse. It's 1 over the determinant. And the determinant of a transpose is the determinant of the original. So, again, we proved that, and now we know for sure that's got to be true, because determinants can be computed using the following formulas. The 2 by 2 matrix determinant must be the magic number AD minus BC. We established that by verifying that this indeed is a row linear alternating and identity preserving process. And then we established why these recursive formulas end up working the way they do, and we noted and we proved that it doesn't matter if you use which row or which column, you will always get the same result. And again, that came from this fact right here. All right, cool. All right. Well, now that we've established that the determinant exists, it has all of the wonderful properties we want it to have, and furthermore, we have these formulas for computing them. Now the question of the day is, alright, we've got this, so what else do we do with it? And there's two classic applications of all this fun stuff. So first off, we're going to get, as promised, the formula for the inverse of an n by n matrix. Now, in order to do that, we first need to prove a little side result here. Let's say you have a distinct row and a distinct column, and let's say you were going to do your recursive formula. You delete your qth row, and you're just going down your columns. Let's say that instead of multiplying by the correct entry, the qth entry, you were a big dum-dum, and you multiplied by the pth entry instead, which is different from q. Well, all is not lost, because that actually just so happens to equal 0, which at first glance seems like a pretty crazy result. Like, how the hell is this true? Basically, you went for your formula and you goofed up and multiplied by the wrong thing. Note that you kept the minus signs correct. But it just so happens it's equal to 0 because if you set up the correct matrix, all of this just pops out for free. So in particular, let's let the matrix B be the matrix A, only I've replaced the qth row of B with the pth row of A. So the matrix B has two copies of the pth row. Alright, so then if you look at the determinant of this, and here we're making sure that we appropriately use the qth row, well, this matrix has A in its pth row right there. Now, note that if you are, note that this pops out from this right here. So now a couple of things. So our matrix B has two identical rows, P and Q, so its determinant must equal 0 by the alternating property. And furthermore, if we're deleting the qth row, well, we're deleting the row where we did something different, so all of the other rows A, so when I delete the Q for O, I just get A if I delete its Q for O in kth column. So this right here will simply equal that, and the desired result follows. So we get what we wanted. So this one has always been a really neat little fact to me. So note, you have this use the alternating property of determinants. Determinants equal to 0 for two matrix with two identical rows. Right, but it's kind of a funny result that you get 0 if you do the recursive formula for determinants, but you screw up what you multiply by, and you just get 0 instead. So it's really neat that actually equals 0 rather than nothing. Again, another sort of cursed result, but a very powerful result because, hey, if the P and the Q are different, I get 0, but if the P and the Q were correct, I'd get the determinant. So if the P was equal to Q, on the diagonal of a matrix, I'd have the determinant, and if they're different, I'd have 0. Wow, that sounds a lot like a scaled identity matrix. Well, given matrix A, its adjugate is defined as follows. You do -1 to the j plus k, and you multiply by the determinant, but note here the determinant we've swapped. So the jkth entry is the determinant of the kth row deleted and the jth column deleted, and then a -1 to the j plus k. So note it's kind of the recursive formula, but some ingredients are missing. Now this is currently known as the adjugate. If you go back in the day and look at a really old linear algebra book, they would actually call it the adjoint. However, it turns out that there is a more appropriate thing to call the adjoint in the context of linear mappings. And we will see that a little bit later when we get into inner product spaces. All right, give me a second. I have the answer text. This is the lunch plan. Sorry for the interruption. Because once I was done recording. All right. Back at it. Okay. So, like I was saying, this is called the adjugate now, but in older books it was called the adjoint. But as we'll see, there's a better thing to call the adjoint in terms of matrices rather than this thing here. So it's now been denoted as adjugate. Still the ADJ, so the old notation is still going to come through. All right. So, let's prove, as promised, that there is a matrix B, so that A times B is equal to the determinant times the identity. And life is good. Sorry, more text. All right. So, let's actually go for the proof of this. Now, the proof of this is particularly easy, and note as a wonderful consequence of this here, you actually have the formula for the inverse. It's 1 over the determinant times the adjugate. And, hey, that looks a lot like the formula for the inverse of a 2 by 2. So, indeed, you can go through and verify that the swap the diagonal and negate the off diagonal is in fact the adjugate. Excuse me. By, of course, going through the usual delete the row in the column, and the fact that the 1 by 1 determinant is just whatever the entry is. It's the only thing that could possibly be real linear, so, Alright, and identity preserving, gotta throw that in there. The alternating, of course, does not apply. Anyway, alright, so, let's go ahead and go for the proof of this. Now, note, the adjugate is kind of part of it, but it's missing something. It's multiplying by the entry and the summation. Oh, really? Good thing the, matrix multiplication is going to multiply by entries and add it all up there for us. Indeed. So if we look at the PQ entry of A times its adjugate, I get, of course, the matrix multiplication formula. The JQ entry of the adjugate is the -1 to the K plus Q, and then you delete the Q row and the K column. Here I swapped the Q there, so that indeed what I'm going to get is just the normal formula for determinants. And oh, wouldn't you know it, hey, I'm trying to do the recursive formula, but I goofed up and multiplied by not the right entry. Well, if I am multiplied by the right entry, I'll just get the determinant, which means that I've got the determinant times the identity matrix PQ entry. And if I pick the wrong P, I get 0, as we proved. And there you go, the PQ entry of A times the adjugate is the PQ entry of the identity times the determinant, so the desired result follows. Multiplying by the adjugate simply gives you the identity matrix scaled by the determinant. Beautiful. And there you go. You now have the formula for the inverse of any size matrix, and the first problem on the exam is definitely not going to be compute the inverse of a 3x3 using adjugates. Oh, so let's get an example of that for no particular reason. So, hey, you got this matrix here, -3, -5, -7, 2, 4, 3, 0, 1, 1, and that last one's negative. Okay, well, the determinant of this is -3. It is, trust me, I did it. And the adjugate can be computed as follows. So again, note, we get this entry by deleting row 1, column 1, taking the determinant, what's left over. And note that that is going to be a plus. This entry here is the 1, 2 entry, which means I delete the first column, second row, and take the determinant of what's left over there. So that will be the 5 plus 7, giving me positive 12. But note this will be negative because I'm in the 1, 2 spot. And then you can run through and compute the rest of this to verify that it is indeed correct. And scaling this matrix by -1/3 then gives me the inverse of my matrix, and there it is. Beautiful. All right, pretty cool. Pretty neat right there. So that's kind of a nice little result. And of course, this will let you compute the inverse for any size matrix, but of course, it's computationally very intensive because, again, you're computing determinants, and that's recursive. And for a 3x3, it's not too awful to do by hand. It's still a lot of things to do. But of course, for 4x4s, 5x5s, since the determinant is going to be factorial, I mean, just a 5x5, forget it. It's insane. It's an insane number of computations. But we got a formula for it. It exists. There you go. You got it now. Everyone's happy. All right, so as promised, 2 things that we're going to hit today. The first one being the adjugate. Next up, an oldie but a goodie, good old Cramer's rule. All right. Now, before we get into what Cramer's rule actually is, we need to set up some machinery. So in particular, given a matrix A and a vector B out of Rn, we're going to let A sub k of B denote the matrix obtained by replacing the kth column with B. All right. Now, again, this is a matrix operation that can be performed, and there's not particularly some standard notation out there for it, so you either just say that the matrix I'm dealing with is this one, or you come up with some goofy notation for it. This is a notation that I've seen in several places, so it's the one we're going to use. Now, of course, you might want to have a notation for replacing the jth row with a vector. Sure, come up with one. Enjoy it. Anyway, this is the notation for replacing the kth column with B. Now, this particular thing is going to be very powerful and very useful if we're trying to solve AX equals B. Because if I have a n by n matrix, and I know I have x and b satisfying ax is equal to b, then this matrix right here is obtained by taking the matrix A and multiplying it by the identity matrix, where you've replaced the kth column with x. Nice. So in other words, it lets us basically rewrite this formula in terms of this. And this is pretty easy to show because pick any j. If j is not equal to k, then the jth column of A times this matrix will be A times the jth column of the matrix on the right. But this is the identity matrix where I've replaced the kth column of X. If j is not equal to k, well then I just get the jth column of the identity matrix, which is the standard basis element EJ, and multiplying by that gives me the jth column of our matrix. And when j is equal to k, well, then the jth column of this is x, and by hypothesis that is equal to b. So there you go. Pretty good stuff. Person seen, front doorbell. What's that nonsense? Oh man, a lot of interruptions in this video on my freaking cell phone. I gotta see who's casing the joint. That was Amazon. Yeah. What is? Oh, I know what that is. Ooh, Ashley's gonna be very excited about that one. All right, cool. All right, so hey, this whole replacing the column business, we now have a multiplication representation for it. And again, we see that a lot of matrix maneuvers can actually be written in terms of matrix multiplication. Row operations, deleting rows, deleting columns, as mentioned previously. And now here we see replacing a column can be also written in terms of a matrix multiplication involving a modification of the identity matrix. Quite nice. All right, so how are we going to use this with determinants? Well, the key ingredient to this is that the determinant of the identity matrix, where I've replaced the kth column with x, just gives me the kth entry of my vector. And this pops out pretty easily out of the recursive formula, because look at the determinant of that, you get this mess of things, but let's just go through it. If the j is not equal to k, what happens? Well, this right here will just give us the identity matrix, but j is not equal to k, so we get 0, so all of those terms are dead. So I only need to look at the kth entry, so that's the -1 to the k plus 1, -1 to the k plus k, and the kth entry of this, and the delete the kth row and column of that. This, of course, will equal 1, because it's 2 k's. The kth entry of this will be whatever the kth row, kth column is. Right, this is the matrix where I've replaced the kth column with the vector x, so I'll pick up x of k. All right, and if I delete the kth column of this matrix, well, that's just the n-1 by n-1 identity matrix. The determinant of that is equal to 1, and there we go. All right, so with all of this set up, we can now state Cramer's rule and actually prove it. So, take an invertible matrix and let A, X, and B be so that AX is equal to B. Then the kth entry of X is computed by computing the determinant of the kth column replaced with B divided by the determinant of the matrix A. Ooh. The classic Cramer's rule. All right, so a couple of things about this before we go for the proof. My professor for this class, good old Professor Fulton, who we've mentioned before multiple times, he had a very strong opinion on Cramer's rule, and his opinion was Cramer's rule is completely and utterly worthless. So we didn't prove it. He mentioned it, and he was like, yeah, Cramer's rule, whatever. If your matrix is anything other than a 2x2, this is completely worthless. And he's kind of not wrong, because while this gives you an alternative method of solving AX equals B, it involves computing determinants, which for anything outside of a 2x2 is a very involved process. So, while it's not numerically the most exciting thing, the proof of this is actually really cool. It's a super neat proof. And so another example of Professor Fulton talking about something and then me later on going like, actually, no, this thing's cool. The proof of this is really cool. I think the proof's really cool anyway, because the proof of this is a one-liner, because we already did all the work. And we'll do an example of how to actually use this to solve a 2x2 using Cramer's rule. But let's get to the proof, which is a nice one-liner here, because if you look at the determinant of A times x sub k, we've already proven this is the determinant of the identity matrix, where you replace the kth column with x. the product of the determinants, the determinant of the products. And, oh, wouldn't you know it, this product right here is equal to that matrix, as we proved. Ta-da, proof's over. So the proof here I really like, because first of all it uses the key property of determinants, that the determinant of the product is the product of the determinant, a very important fact there. And again, it's using the sort of a matrix operation, can be written as a matrix multiplication, a common theme that we've seen now a couple of times. So to me, the proof of this is very valuable. It's got a lot of matrix maneuvers, a lot of common matrix maneuvers on display, and it lets us establish a classic result. And side note about Cramer's rule, Cramer's rule is actually a generalization of the adjugate, because you can actually get the adjugate formula out of this if you do it correctly, because AX equals B, well, if B is the identity, if B is taken to be the standard basis elements, well, then the x's here have to be the columns of the inverse of the matrix, which is the adjugate, and this actually gets you the formulas for them. Pretty neat. So you got to work out, there's some details to work out there, but you can do it. So Cramer's rule is actually, in my opinion, it's an important theoretical thing, and it's actually a generalization of the adjugate, which is a neat little fact there. So I feel like it's a worthwhile thing to prove, although there's no sort of good application of this outside of the 2x2 case, so let's actually do that. So let's say you have a 2x2 system you're trying to solve. The matrix you need is this one right here. The right-hand side is that. The matrix where you replace column 1 with B is this one. Column 2 with that is this one. Compute all your determinants. And then you can solve for x1 and x2 by taking this determinant and dividing it by that. And taking this determinant and dividing it by this. Ta-da! You solved your 2x2 using Cramer's rule. You, of course, can do this for 3x3 and larger, but as noted, computationally that gets a little dicey, so, not necessarily going to do that. Alright, and with that, baby crying, so I gotta go deal with that. Thanks for joining me with our second video. I'll see you in person next time.